This video is going to cover information bias, which is one of the major systematic biases in study design. So it's when you incorrectly specify someone's exposure status, disease status, or really any covariate you're looking at. It's basically just getting someone's information wrong. And when this is a continuous variable like age or height or something, it's considered measurement error, and it's more referred to as misclassification when it's a categorical variable like sex. And it's kind of similar to random error, but it's distinctly different in the sense that random error can be eliminated with an infinitely large sample size, and that's mostly because the error is happening kind of at an equal rate above and below the true value, so on average it is the true value. Information bias can't, and that's because it's a systematic bias. If you increase the sample size, you're not going to correct it. Random error impacts the precision, so like your confidence interval and whatnot. Well, information bias can actually impact the odds ratio or the measure of effect, making it a much more serious type of bias. So there's several sources, and this is going to be a pretty long video just because I got kind of carried away having fun with the visual representations. But yeah, these are the many ways that you can get information bias. Incorrect recall when you're asking someone to say their exposure many years ago. The equipment you're using to diagnose can be inaccurate. You can have leading questions that kind of prime a certain answer. You can have biased interviewers, non-compliance in the case of a random assignment, and also incorrect inference, specifically etiological irrelevance. So I have a video talking about sensitivity and specificity. This is a 2x2 table. It's classic. It's looking at the various combinations of disease status and test status. So at the top left, you have true positives where the test said the person has the disease and they truly do. And at the bottom right, you have true negatives where the test says they don't have the disease and they really don't. But the other two cells are false positives and false negatives. And when it's a categorical thing like sex or disease status, then yeah, this represents misclassification when it's at the bottom left or top right cell. They represent false negatives and false positives. So sensitivity, it's not too important. I have another video on it, but it's basically just the amount of individuals, it's the probability of the test saying someone has the disease, given that they really do have the disease. And specificity is the probability that the test will say they don't have the disease when they in fact don't. And that's not the purpose of this video. This is just kind of showing how misclassification of a categorical variable happens in information bias, and to kind of prime the idea that in a case control study, as far as like figuring out someone's exposure classification, like whether they're exposed or not, that can happen with varying accuracy among cases and controls. And when it's happening with the same amount of error, so exposure is inaccurately measured at the same rate in both cases and controls, that's non-differential misclassification. And that generally is less of a problem than differential misclassification, and that's when the sensitivity or specificity of exposure classification is different among cases and controls. And I have a video on how to do this is like classic on like epidemiology tests doing these classification and misclassification calculations, and they're pretty easy. I have a video on how to do those. So the implications of non-differential and differential misclassification, they're different. They vary in severity. So the major effect with non-differential, that's when like you're messing up on cases and controls to the same degree. It mostly just dilutes true effects, and that's kind of less of a big deal, where like if the true odds ratio was like 2, it would move it closer to 1, and the more it's happening, the more likely you are to not find something. It always biases towards the null. Well, differential misclassification is a lot harder to predict. It can go towards or away from the null. So recall bias is the first type of information bias I'm going to talk about, and that's probably the most important one. If you're ever asked what is like a major drawback of the case control design, that's always a good answer, is recall bias, because with the case control design, the disease has already occurred. People know they have it or they don't have it. And if you're asking them about their exposure in the past, their knowledge of whether they're a case or not might influence the way they remember the past. And it's a form of differential misclassification, and the most severe kind, one of the major reasons that a case control study is considered by some inferior to a cohort study. So I have this situation here where we're looking at radiation and cancer. So at the far left, we have individuals who don't have cancer and they weren't exposed to radiation. This is a case control study where we have these people who do or don't have cancer, and we're asking, like, a bunch of years ago, were you exposed to radiation? So this person at the far left who doesn't have cancer, if they're asked about their radiation exposure, they're likely to correctly remember no radiation exposure. And someone who doesn't have cancer, who maybe worked at like a nuclear power plant, like that second cell, will likely correctly remember they have been exposed. And now at the far right, now we're looking at those who do have cancer, and this is someone who has cancer and was exposed to radiation. They're likely to correctly remember. But where it gets interesting is when someone has cancer, they know they have cancer, and they're looking for reasons why. We might ask them, were you exposed to radiation? And they might say yes. In reality, they weren't. But because they have cancer, they might be more likely to say they were exposed to radiation, when in reality they weren't. And that might be because they have some understanding that there's a relationship between radiation and cancer, and it subconsciously makes sense to them that they must have been exposed to radiation, and that's why they have cancer. And the reason that can't happen in a prospective design like a cohort study is that they have no chance to state their exposure in the context of a disease status, because the disease hasn't happened yet in a cohort study. But here, people who have the disease might be more likely to remember exposure incorrectly. That might be overestimating or underestimating, but it's just more likely to be wrong in a way that is dependent on outcome status. Differential follow-up vigor is a big one. So let's just say there's an interviewer asking about coffee and insomnia. If this person already knows, like this researcher, that the individual doesn't consume caffeine, and they ask, do you have trouble sleeping? And the person replies no, they might be less likely to ask further questions. But if they know that this person does consume caffeine, say that was the previous question, and they ask, do you have trouble sleeping? The person says no. They might have this idea in their head, this researcher, that they must have trouble sleeping. They consume a bunch of caffeine. They probably just didn't understand the question. So they might ask more probing questions like, do you wake up a lot in the night? And they might say yes, and they might then go on to say that counts as trouble sleeping and consider them insomnia positive. What happened there was there was differential vigor with which they pursued the answer depending on exposure status. So in that way, if someone consumes caffeine, they're more likely to detect the outcome, and in that way, information bias, this true value of insomnia positive or negative, is more or less likely to be found whether your exposure positive or negative, and that's through differential follow-up vigor or differential questioning vigor. Social desirability is a big one. If you're asking people questions about things that have like socially acceptable implications, they might be more likely to lie. So if you're asking them how often they exercise and they don't exercise a lot, it's possible they might say they do just because they think that that's the socially acceptable answer. Same with diet. They might in fact have a bad diet, but if you ask them that, they might report their diet as better than it is. And in that way, that's information bias, because their diet or exercise status that you're recording is different than it really is. Interviewer biases are a big one. It's not a huge deal when you have like a team that really buys into the research process. They'd leave their biases behind, but it's possible the person might have bias. So here, this is like a question. If like this person who's like visibly a hippie is being asked, do you smoke pot, or how much do you smoke? They might say they don't, or they might say some low amount, and the researcher might have preconceived notions about this person with like long hair, headband, peace sign, and they might write down that they smoke more pot than they said they did, and that's them letting their biases taint how they're recording information. Another thing is leading questions. So asking a question in a way that might influence the answer. So if we have this religious person saying, like, are you against this barbaric practice of abortion? Framing it that way might make someone feel attacked, and they might lie about their opinions on abortion, when in reality they might be pro-choice. But yeah, the way you frame a question might influence the response. Blinding is a big one that a lot of people have heard of. That's common in randomized control trials. It's basically limiting who has what information on treatment status or outcome status, or really anything. The most common one is blinding participants, and this is done with a placebo. So this is an example when the participants weren't blinded. So this person was just told, you got the treatment. And they might use this information now that they know they got the treatment, and that might taint how they report how they're feeling. They might say, that's why I'm feeling good. It might it might give them more like hope. It might make them feel more optimistic. Also, as far as side effects, that might lead them to take some vague symptom like a headache that could come from all kinds of things and attribute it to the treatment. If we tell people they got the placebo, that defeats the purpose of a placebo, but that might cause them to feel less optimistic. I might say that's why they're not feeling any better. The way to get around this is to not tell them what they got. Just give everyone a pill. One of them's a placebo, like a sugar pill or just a shot of water or something, and you ask them how they feel, and they're more likely to give a more accurate representation that isn't influenced by their knowledge of the treatment. And now blinding researchers in addition to those who have the two participants is a good one. So if the researcher already knows what the person got, that might taint their answer. They're saying the participant doesn't know. This is an example where the researcher hasn't been blinded, and they are thinking in that thought bubble that this person got the treatment. They look better. That like their knowledge that this person got the treatment might taint how they record information or ask information. Another big one is blinding analysts. If you ever hear of a triple blind test, that means or a triple blind study, that means that both the researchers, the participants, and the analysts are blind. What this means by blinding the analyst here is that we have two analysis. Analysis 1 here at the top, you can see that the treated group did better than the placebo group. But if you choose to do the analysis multiple ways, you might have one analysis that has a significant effect and one that doesn't. That's one of those things about statistics not a lot of people know is that basically like you can choose a lot of routes of analysis and they might get varying answers. If this person knows which is the treated and placebo group, that might taint their decision. They might say treatment 1 is significant in this analysis 1. We should use analysis 1, and that would be foul play in the sense that it's possible analysis 1 might have more problems. But if we just label these groups A and B, and the analyst doesn't know which one is the treatment group, and they can't bring their desired outcome and let that influence things, they might say something is significant in analysis 1, but analysis 2 is better. It is more sound. And that way they might choose analysis 2 and not let their knowledge of whether what they wanted to see is there. They won't let that influence things. So as far as continuous measurements, here we have a line of agreement between a measured and true value. This line represents perfect agreement. There's likely to be variability around the measured and true values, this kind of random disagreement. And this is a good representation of, you can see that like it's above the line about as much as it's below the line. So if we had like an infinitely large sample size, then it would even out. Another situation is if it's systematically above it's systematically overestimating or whatever. Yeah, if it's wrong in a systematically consistent way, that's not a huge issue if that is evenly happening among cases and controls, because in that way this error is equally imposed on the control and case group, and basically that would lead to a compensating situation where you might actually get a valid effect. It becomes more of an issue when you can see now here the blue individuals, the control individuals, are more often incorrectly estimated, while those red individuals are more often right on that line. It's more often true values. So in that way, that's differential because it's happening to controls more than cases, and that would be information bias in a more egregious way. This is still information bias over here, but it's not necessarily going to change the odds ratio. Well, this one's more likely to change the odds ratio. This is another situation where you can see at at lower measures, like when at lower concentrations or whatever this is, there's more agreement between the test and the true value. But as the measured value gets higher, it's more likely to deviate from the true value. And if this is like some continuous exposure variable where we pick some cutoff where once you cross it, you're exposure positive, that can become an issue. Like over here where we see we're arbitrarily defining people to the right of this vertical line as exposure positive, but they in reality like have their true value for most of these people who are considered both exposure negative and exposure positive. Most of them have the same value. It's kind of arbitrary because this measured value isn't trustworthy beyond where these two lines deviate. It's a little more complicated talking about continuous measures, but I was hoping to try and make that clear. Non-compliance is a big one with randomized control trials. Here we have the exposure group, those blue ones, and the exercise group, and the non-exercise group, the group that's colored black there. Here, if they're followed over time, it's possible. You can see that one of the people in the non-exercise group moved to the exercise group, and some people in the exercise group moved to the non-exercise group. Non-compliance with initial treatment assignment is really common. Intent to treat analysis is the gold standard, where even though we recognize that people switch groups, we analyze them like they didn't. And although that imposes information bias, where there's some people that we're calling them exercise because we assigned them that, but they changed groups, that counts as information bias, but it's considered actually the better option than analyzing people in the group they ended up in. I have a video on non-compliance that explains that, but basically that's an example of information bias. An error in inference is probably one of the most important, but the hardest to conceptualize, and that's like if this is just representing like the course of a disease. So if we're looking at like the relationship between some exposure and some disease, the course of events would be you'd have your first contact with this exposure, and then there'd be some amount of time, like a number of cigarettes or number of x-rays or some sufficient exposure that triggers some event. Like cancer is the easiest one to talk about, where like, let's just say this is your first cigarette, this is some like 10,000th cigarette, where it puts this like process in motion where you're not going to get cancer the next day, but cancer is occurring. And then this is the exposure period, the time you're accumulating exposure. And then the next thing is disease onset. Like I said, it like once you trigger this sufficient exposure, this series of events, like some oncogenic process goes into motion. And there's a little while until the actual disease happens when that first cell becomes cancerous. And that's called the induction period. And then between disease onset, there's a time between when symptoms happen and when you're ultimately diagnosed because of those symptoms. And that is the latent period. Okay, so with all that, as far as talking about inference, let's just say we're looking at smoking and lung cancer, and between this first cigarette, the furthest to the left, and when there's a sufficient number of cigarettes, if someone gets lung cancer in that window, can we really attribute it to smoking? They've only been if someone's been smoking for 2 weeks, are they really exposure positive? So that's something you got to think about, where like when you're determining if you ask someone, are you a smoker? That might not be a good enough question to determine whether they're actually exposure positive. You might need to come up with some cutoff. Like you might need to say, like, have you been smoking for this long? And a similar one is, this is an example of like cancer following the Chernobyl disaster in Russia, where like if we have this meltdown, this event where it's both the first and sufficient exposure. Like if you were part of the Chernobyl disaster, you've been sufficiently exposed, but it's still going to take a while for cancer to develop. So if someone's diagnosed with cancer the day after the Chernobyl disaster, it's between the sufficient exposure and when disease onset is expected. It's during this induction period where, although this person has been sufficiently exposed, they were exposed yesterday, and it's physically impossible for them to already have cancer from it. It's going to take a while, and in that way, that's a type of that's a type of information bias if you make that error, basically.